All right. So where we last left off, oh yes. So the project two is due tonight at the usual 1 second before midnight. And with any sort of Wireshark or any Wireshark project, please include screenshots with supporting material for your answers. It shows me where you got your answer, but also if you forget something, it gives you an opportunity to get partial credit because I can see information in the screenshot. Okay, so the project two is due at the usual 1 second before midnight. Question? Sure, sure, but I disappear at this after a certain point because I have another class at 4:30. But yeah, I'm also available via Slack and all those things. Okay. All right. Any other questions? Yeah? All right. So So we last left off, we talked about DNS a little bit. So we'll pick back up with that. And we said DNS is a distributed database. And as a database, it associates data, i.e., the string domain name, with other pieces of data, namely the IP address. Now, certainly, when you enter in something like www.disney.com or desu.edu, that name is really only there for our benefit. All the machine cares about is that IP address, right? And in fact, you can enter in an IP address in the URL field for your browser, and that will work perfectly well. And the machine actually doesn't care about this string. That's for our benefit. And so this database is not a singular database. It's distributed, so it exists in a bunch of different places. And each one of these databases collectively form a hierarchy in order to organize all of the many domain names you might have. So if you think about it, there's desu.edu, there's disney.com, there are domain names with .net on the end of it, and for various countries they have like .jp for Japan and so forth. There are all sorts of domain names, and whenever you have a large number of things, it's a very wise decision to organize or associate them with one another in an organized way so you can more easily access them. And that absolutely is what was done with DNS. And so at the top of the hierarchy is the so-called root DNS servers. And the root DNS server you can think of as being associated with the nothing domain name, right? It's the root of the hierarchy. And so every single query or question you're asking of a DNS is you're trying to say, well, here is my text description, my domain name. Please give me the corresponding IP address. And so that's called a query. So when you resolve a DNS query, you're submitting a domain name to DNS system, and you're asking it to give you back an IP address associated with it. And that's what you get in return. And so the root DNS is where all queries go. And right underneath the root DNS are a set of servers, and more correctly, there are a bunch of data centers that manage domain names with certain suffixes on them. And so the so-called top-level domain, or TLD domain name server, corresponds to that last part of a domain name that ends with a dot and some string, right? So if you had Disney.com or IBM.com, all of the .com domain names are managed by the .com top-level domain name server or the .com TLD server. Likewise, there's a separate domain name server for the .edus. So any university or any school or concern with a .edu, desu.edu, pennstate.edu, umass.edu, what have you, they're all managed by the .edu TLD or top-level domain name server. And so as you see these new domain names come up like .mobi, .me, all these other different things, certainly there is a top-level domain name server associated with each of those groups of domain names here stylistically. And so we have our TLDs, and below the TLDs are the particular DNS servers for the organizations, and those are called local DNS servers. And so the local DNS server in the EDU case, if you take umass.edu, well, at UMass, University of Massachusetts, there is a domain name server or set of domain name servers that will hold all of the IP address mappings for anything that is a .umass.edu. So if you go to CS for computer science, cs.umass.edu, it is the DNS server, the local DNS server for UMass that will have the name IP address mapping database DNS server rather for all of the machines that are identifiable and managed by UMass. Okay. All right. Any questions about this? Okay. So we have this hierarchical arrangement, and when you issue a query, query first goes to the root server, and that root server looks at that extension .com.net, and it consults the TLD server, the appropriate one, for further delineation of what that right mapping is. And if it sees umass.edu, the edu server, it knows what all of the individual edu DNS instances are. And then it forwards that request ultimately to umass.edu's DNS, and it gives you back the IP address. So let's take a look at how this might work, continuing on. So the root name server, now, of course, this DNS root server, all queries, all things being equal, go through the root DNS server, but certainly there are some optimizations that occur because you don't want that single point of failure. But nonetheless, the root servers for DNS are distributed all across the world, and they exist in the form of a set of data centers. And so this map is not current by 2020 standards, but it still illustrates the point, and it lists a bunch of locations where you find root DNS servers. And so this root name server is going to contact the authoritative server, and the authoritative server is the server that owns the name to IP address mapping, but it does so indirectly going through the TLD server instances. And so when we talk about root server, it's called the root server, but it's not really a singular server. It's a set of data centers that themselves are distributed throughout locations in the world. Okay, so the TLD servers are responsible, as I said before, for that first part, that suffix on the end of a domain name. And that's just really for our purposes because we like to organize things, and that does two things. It makes it easier to manage, but it also distributes the load. And so the TLD servers are managed by certain organizations. So Network Solutions, which is a concern in the greater DC area, they manage the .coms, right? Educase is an organization that manages the .edu domain names. And of course, with enough looking, you can find out who manages the .mobi, the .me, and all those other things. And so the authoritative DNS servers are usually those local DNS servers managed by a local organization. So somewhere on campus, there's Delaware State's DNS server, and Delaware State's DNS server contains, it's the authority for the IP address to name mapping associated with all the host names that are managed by Delaware State University. And so let's take a look at this hierarchy. And so the DNS itself, when you have a local DNS, it's often called your default name server. And so one of the bits of information you need when you attach a machine to an access network is you need the local DNS so that you can look up domain names and get them mapped to IP addresses. And so the reason why when you specify www.disney.com or the website for Zig and Sharko, the reason why you can contact them is you are first accessing your local DNS. And so you'd ask your local DNS here at DSU, please give me the IP address for Disney.com. And it says, I don't know. But I will forward on your behalf, the local DNS does this, I will forward your request to the root DNS server, and that request will then get forwarded around to the TLDs and to the local DNS servers until it ultimately finds that name IP address mapping. Okay, so there are two different ways of so-called resolving your domain name into an IP address. One is called iterative querying, and the other is called recursive querying. So I'll first show you what iterative query looks like. And so with iterative query, essentially, when you contact a DNS server, everything is done to your local DNS, and that local DNS acts on your behalf. And when that local DNS server acts on your behalf, it is forwarding your query first to the root DNS server, and when a root DNS server tells it where to go, it forwards back that so-called forwarding address, or returns that forwarding address to that querying local DNS. And then that local DNS does the work itself in going to that forwarding address to contact it to try to find ultimately what it will get as the name IP address mapping. So in this diagram, we have two machines. One is at cis.poly.edu, it's a university in France, and the other is gaia.cs.umass.edu, which exists on UMass Amherst's website, and it's the machine that you connected to for one of the Wireshark labs. Okay, so we also have the local DNS server for Polytech, for Poly, and we also have the authoritative, which is the local DNS server for managing the name IP address mappings for UMass, in particular UMass Amherst. We also have the top level domain name server, the TLD DNS, and that is particular the TLD DNS server for the EDU domain names. And then at the top of the hierarchy, we have the root DNS server. So the first thing that happens, you type into your browser, you're at Polytech here on the lower left in this diagram, and you enter in www.gaia.cs.umass.edu. So the first thing that happens is your browser wants to do a DNS resolution, so it contacts the local DNS at Polytech. And so this local DNS server looks in its database, and certainly it doesn't manage any domain name mappings for UMass, so it says, well, I don't know. Let me contact the root DNS server. So the first message is for your requesting host application. It goes to the local DNS server, and either that local DNS server has that name address mapping or it doesn't. If it doesn't, the first thing it does is it contacts the root DNS server. That's our second message. And it contacts the root DNS server, and it asks, do you have the IP, the domain name IP address mapping for gaia.cs.umass.edu? Now, the root DNS server, it does not have it, but it sees that this domain name ends in .edu. And it says, okay, well, this is a .edu address. I don't have this mapping, but this TLD for edu domains should know what that is because the domain ends in .edu. So it responds back and has a forwarding address that says, if you want to find something that is an edu address, gaia.cs.umass.edu, then you need to contact this particular server, and it gives it the IP address for the TLD for the EDU domains. So then your local DNS server gets that response back with that forwarding address for the TLD for the EDU, and it contacts the TLD server, top-level domain name server, for the EDU addresses. So it says, okay, well, I was told that you have the IP address mapping for gaia.cs.umass.edu. Can you please give that to me? So the TLD for the EDU says, well, I don't have it, but I see that this says UMass, right? I know for a fact that UMass's EDU server is the following. So while I don't have that mapping, you need to contact the authoritative DNS server for UMass, okay, because it's a UMass address within the EDUs. So the EDU TLD server returns back that forwarding address for the authoritative DNS for all umass.edu addresses. Okay, so the local DNS gets this, and it contacts then, using that information, that's the sixth message that goes across, the authoritative DNS for umass.edu. Now that umass.edu says, oh, gaia.cs.umass.edu. This is the IP address associated with that domain, so it returns back that name IP address mapping to the local DNS for Polytech. So now Poly takes that message and it returns it back to the requesting host, and now you get that IP address, and now you can create that TCP connection to talk to gaia.cs.umass.edu. Now, certainly, this is a lot of messages that go swirling back and forth. And so an efficiency that's implemented in DNS servers is that in addition to forwarding you back this eighth message with the name IP address mapping for that endpoint you're trying to contact, it also caches or stores locally a record of information, which is that mapping directly to gaia.cs.umass.edu. Now, this is based on the principle of gossip, meaning that two entities that communicate will tend to communicate more in the future. So subsequently, if you're going to contact gaia.cs.umass.edu, at some point in the near future, you're probably going to contact it again. So because this local DNS server, when it got that name IP address mapping for gaiacs.umass.edu, it caches it locally. So any subsequent request message that you make, you initiate your first message to the local DNS server, and now it takes that cached copy of the name IP address mapping and returns it back directly instead of going all the way around to the root, to the EDU, and then to the authoritative for UMass. Does that make sense? Any questions? Yes. Ah, it's the same idea in terms of caching, but it's for use. I'm going to say yes with a little asterisk, right? It's caching in the sense that it's storing something locally instead of going back across the wire, but it's using that caching for a different purpose. So yes, absolutely, but it's not for the purpose of saving round trip time for origin server. It's to save the set of iterated lookups that you have to make, and you go directly here on subsequent connection requests rather than waiting on the local DNS to propagate all these messages back and forth. So yes, it is caching, but it's not the same type of caching. Okay. Any other questions? Does that make sense? So that's iterated query. Let's look at the other type of query, recursive query. Now, of course, when you set up domain name servers, if you administer or quote unquote own the network, you can decide what type of querying your DNS supports. Now, certainly you could have an iterated query, and once you're inside of an organization, that organization can subdivide however they want to. So inside of umass.edu, they could have a separate DNS server that UMass's DNS contacts for everything in natural science and math college, everything in arts and humanities, everything in athletics, and so forth. And so when you get inside of an organization, yes, there's an authoritative, but this authoritative can be at the root of yet another hierarchy that splits up all the domain names within an organization. Okay, so what is this recursive query? So with recursive query, the burden of contact for subsequent contacts through the hierarchy is placed on that server that is contacted, right? So what does that mean? So if I contact you to look something up, if you don't know, tag you're it, now you have to go out and get that other piece of information and return it to me instead of giving me a forwarding address and I have to do the work of getting that other piece of information. So let's take a look at the same scenario, but in this case, we have recursive query. So we start out with your requesting host. The first message comes along, and that's for the name address resolution at the local server at Polytech. Now, that server does not know what the mapping is for name to address for gaia.cs.umass.edu. So the first thing it does is it contacts the root server, and that's the second second message that goes out. So the root server, it looks in its database, it doesn't have the name IP address mapping. So it says, well, that has a .edu on the end of the domain name, and I know all of the edu addresses are managed by the TLD server instance for the edu addresses. So now in iterated query, instead of giving back a forwarding address from the root server to the local DNS, it's going to do the work on its behalf. So the root DNS server then contacts the edu server, the TLD for edus, and asks it, do you have a name IP address mapping for umass.edu? And so the TLD for edu addresses, it says, I don't know what that mapping is, but I know because it says umass.edu, I can tell you where to go for the authoritative for all the UMass edu addresses. So now the TLD for the edu does that work instead of putting that burden back to the local DNS server for the requester. So the TLD for the edus then contacts the authoritative for UMass, and then the authoritative for UMass, it has that IP address mapping. It sends it back to the TLD for edu, which sends it back to the root server, which sends it back to the local DNS on the requester side at Polytech. And that mapping can also be cached in storage at the local DNS at Polytech. Any questions about this? Does that make sense? So, there's a lot of stuff going on, and all of that's the beauty of it. It takes a few milliseconds, almost instantaneous. And any subsequent access both in the iterative and the recursive, if you're trying to now, again, second time, access gaia.cs.umass.edu, you're going to use that cached copy of that name IP address mapping instead of going through this whole circuitous route, propagating these messages. Now, certainly there's a drawback with this. The drawback is that you'll notice eventually, if you have an unresolved name IP address mapping, all of those requests are targeted at the root DNS server. Now, of course, you can imagine if you're resolving Disney.com, certainly other people are resolving Disney.com, and every single request that you make to resolve IP addresses, everybody does, is going to go through the root DNS server. And so that appears to put a very heavy load on the root DNS server. And anytime you have a single so-called point of failure, things can be very brittle, even in spite of the fact that it might be a data center rather than just a single physical server. And so this idea of caching records saves a lot of these edges in this process, regardless of if it's iterated query or if it's recursive query. And so if you think about it, on subsequent requests, if we cached at the edu TLD server, we're going to save those two messages to the authoritative for UMass and the return trip. If we were able to cache at the root DNS server, theoretically you could, but in practice you don't, because if you're going to cache at the root, that means every single request is going to result in a cache entry, which sucks up a lot of storage. But nonetheless, if you theoretically cached at the root DNS server, the name IP address mapping between a umass.edu name and address, you're going to save these four edges. These set of edges between the authoritative for UMass back to the TLD for EDUs, as well as between the root and the TLD for EDU. If you cache at the local DNS server, which is typically the case, because that's local, and of course, the burden of storage is charged against the organization that wants to request the mapping. And so you control that, and it's most logical, if you will, to place that cache entry at the local DNS instead of polluting the infrastructure, namely the root DNS and the EDU TLD with this caching ability, although theoretically it is very possible. So if you cache at the local, then every subsequent request, you can have the initiation, the lookup, and the return out of that local DNS instead of propagating messages around the internet. Okay, any questions? And so you can cache records, and that's called learning a mapping. And that's demand driven, right? And so if you need to resolve it, that particular entry is added. Now, of course, this entry that's cached, it has an expiration date on it, so something called a time to live field. And because you don't want these things to sit there forever, because what can happen is someone can actually change the IP address of some internet property, right? Maybe they change service providers, maybe they move, all sorts of things can happen. And so you don't want these name address mappings that are cached to persist ad infinitum, right? You want them to be able to change. And how that's done is by having a time to live field or an expiration date associated with these cached records. Okay, any questions about this? Does that make sense? Okay. So let's take a look at what these records are. These are so-called resource records. And these resource records are the unit of transfer and unit of storage for all DNS questions, DNS results for queries, as well as storage of DNS name IP address mappings on cache storage. So this is what the resource record format looks like. It's a 4-tuple, and the first field is a name. All right, so it's a name value pair, and the second field is the value, and this third field is a so-called type. Now, depending on what this type field is, the interpretation of the name and value is going to be different. And then lastly, this last field is the time to live, which is our expiration date. After the TTL amount of seconds has gone by, then this record is no longer valid, and every DNS will not use it. It'll go out and fetch a new one. Right? So this particular quote-unquote cache, it has a time associated with it, this cached entry, and based on that time, the DNS will make the decision as to whether or not it's going to reach back across the internet infrastructure and get a new one, or if it's going to use what has been stored locally. And so here we have 4 types of resource records, and these are different values that the type field can take on. The first is called a type A record or an authoritative resource record. Now, when the type is a type A, the name is considered the host name, right? Like IBM.com, Disney.com, and the value is its IP address, like 204.18.37.2. I just made that number up. Somebody has it, but I have no idea who it really is. If it's a type NS for name service DNS resource record, the name is a domain name, right? A domain name is different from a host name. A domain name aggregates a set of hosts. So you have gaia.cs.umass.edu. In fact, you have cs.umass.edu. cs.umass.edu is a subdomain within umass.edu. So the domain name is umass.edu. That's the point of entry into the local DNS hierarchy at University of Massachusetts. And when you say NS, what you're doing is you're defining an association between the host name that is responsible for name IP address mappings for that domain and the domain name itself. And so a type NS resource record interprets the name as a domain name, like IBM.com, like umass.edu, and the value is the host name of the authoritative DNS server instances, the host name, not its IP address, but the host name. So for example, you might have a name like umass.edu, and then the value would be dns.umass.edu, for example. And that's a type NS or name service DNS mapping resource record. The other type is the so-called canonical name or CNAME resource record. For the CNAME resource record, the name is going to be an alias for a canonical or real name. And this is how you do things like load distribution. So suppose you had IBM.com, but the canonical name would be East Coast Mid-Atlantic.ibm.com. Now, what the CNAME does, it allows you to distribute your load so that you can designate a set of servers under as if they were a single image or a single internet property. And so for a type CNAME, the name is the alias. That would be like saying IBM.com. And the canonical name is the actual name of the server instance, server east backup2.ibm.com. The value is the canonical name. Okay, and then lastly, there's a type MX for mail server, and oftentimes people want to be able to resolve email IP addresses for email servers running SMTP without necessarily doing funky things with the domain, because you like to be able to email things to, John Smith or Mary Jones at IBM.com, not Mary Jones at mailserver.east.midatlantic.ibm.com. That looks weird, right? And so what this MX record does, when you set an MX record type for a resource record for DNS, the value is the name of the mail server associated with a particular name. And so this is special. It allows you to say, for IBM.com, when it's email, the domain name, it looks like IBM.com, but under the covers, it's really something else. Does that make sense? Any questions about this? Okay. So the resource record, you might have seen when you're running Wireshark, you might have seen DNS query entries, and you can actually look at the resource records in a DNS query. Okay. So what does it look like in the protocol? You have a query, and a query is like asking a question. NS lookup, when I did that from the command line, I'm accessing the DNS system, my local DNS, and I'm entering in a domain name. And in doing so, I'm asking for certain types of results from this DNS hierarchy. And so what the query looks like, we have some bits of identification and some flags to control whether or not this message going across is a query or if it's a response. And you can actually see this information in Wireshark. And it also asks if you want recursion, right? Or if recursion is available, bless you, if you're going to make use of recursion, right? Or whether or not a reply is authoritative. Now, you might ask, why do I care about a reply being authoritative? Remember, the authoritative server is the owner, the prime ground truth of what the name IP address mapping is. Another way you can get name address resolution is because somebody has a cached entry, right, along the route. So oftentimes it's really, really important to know if the name IP address mapping is somebody else's cached copy or if it is actually the response from the authoritative. And that's also encoded among the flags that control the queries and responses. So in the response message format, you also have a set of resource records that are the result of the lookup associated with your DNS. You can have more than one in the response. And so you have the name and type, you have the number of answers, and then you have the records collected together within a packet or of information as your response that comes back across the wire. So if you actually look, you can actually see in Wireshark a DNS request, and you can actually see the DNS responses. And that's how you get access to the IP address, you being the requesting client. And all of that is triggered by the local client's interaction with its local name server. Okay, any questions about this? Does that make sense? Yeah? All right. So let's take, for example, you purchase a new domain name. Now, of course, well, it's not completely that straightforward. Let's say your last name was McDonald and you opened up a restaurant and you wanted to call it McDonald's Restaurant, right? If by some miracle of happenstance, if the large franchise burger operation forgot to renew their subscription on ownership of the domain name McDonald's.com, you could go in and just buy it, right? It's first come, first serve. And open up your restaurant. Maybe you want to open up, I don't know, a pizza shop, and you want to call it McDonald's because you're entitled to call the restaurant after your name. Now, yes, it is free and open property. It's first come, first serve for who purchases it. But I promise you, McDonald's will take you to court and say that's ours, right? Now, certainly you might be right, but if you can't afford as many lawyers and drag it out in court long enough, as long as McDonald's, then even if you're right, you still lose. But nonetheless, outside of those situations, any domain name that's available, you can absolutely purchase. So the first thing you would do is you go to a so-called DNS registrar, and you look up a domain name that you're interested in, and they will say, this is the price, it's open and available, and you say, okay, I'm going to buy it. Right? You go ahead and you buy it, enter in your credit card information and all that good stuff, and all of a sudden that's now your domain name. And so now that you've purchased the domain name, you own that internet property, so to speak, but now you need to make it available so that others can connect to that server identified by that domain name. So whether you host that machine yourself, or most people buy internet hosting, you can get it for as little as $2, $3 a month to as much as hundreds of dollars a month. You'll always be able to pay hundreds of dollars a month for just about anything. But nonetheless, you get a server, and that server will be associated with an IP address. So now you need to advertise the association of the IP address with your domain name. So the first thing you need to do is you need a domain name service. You can use the domain name service of your service provider, or you can install your own. I don't recommend installing your own. There's nothing special about it, but it's a pain in the butt to do it, and it's very cheap these days to use someone else's DNS. It usually comes with a hosting account. So what happens when you get a hosting account? You say, okay, well, I want to insert in your domain name server, I want to insert a mapping, an NS record, that will say where to go if you want to contact my server, say networkutopia.com, what DNS server you're going to contact. So then you're going to insert an NS resource record, and this isn't completely correct. You're going to have a TTL field, but it still illustrates the point. So the name is going to be networkutopia.com. The DNS host name is going to be DNS1 networkutopia.com, and of course it's an NS record, and you're going to have a TTL, time to live field. So then, in addition to this NS record, you're going to insert into your registrar's system, DNS, the authoritative mapping for your DNS instance, because you have the host name, but you don't have the IP address for your DNS. And that's the DNS that people are going to contact when they want to resolve IP addresses for networkutopia.com that you just created. So then they'd have an authoritative record, a type A record, and of course the name is going to be the domain name, the DNS, and the IP address is 212.212.212.1 in this example. So now anyone who wants to go to my website, .networkutopia.com, the first thing they'll do is they'll hit or query this NS record, and they'll say, oh, it's a networkutopia.com address. I need to go to that dns.networkutopia.com. Let me resolve that address so I can get the name for what I'm trying to look up inside networkutopia.com. I get that authoritative record. Now I know the IP address of the DNS for networkutopia.com. I contact it and ask it, what is the IP address from my site, .networkutopia.com? It says here it is, and then you connect and communication happens. Okay, any questions about this? Does that make sense? So it's a lot of interworking parts, but the cool part is we have tools in Wireshark that we can use to actually visualize this, at least within the network on campus. Okay. And likewise, you can also set up the mail server record, but I'm not going to talk too much about that. Okay. Any questions about this? No? All right. So DNS is a vulnerability that people like to attack, and I shouldn't say it that way, a vulnerability, but if you can control how people associate names with addresses, you can actually do a pretty good job in trying to attack a network. And so one of the things you can do is launch a distributed denial of service attack. If you can bombard the root DNS servers, no one can resolve names, right? Same goes for the top level domain name servers. Okay. You bombard the TLD servers, that's a little bit more dangerous. The root servers are very widely dispersed, and there's a lot of caching that happens. But bombarding a TLD server can be more dangerous. You can launch a redirection attacks. And so you can sit there, listen on the network, just like you can see it in Wireshark. You can write a program that sniffs the network, and when it sees a DNS request, it responds. So let's say somebody's trying to resolve what is the IP address for WSFS.com, the bank. So all of a sudden, your machine is listening. I hear that. That's a bank. You have a database of banks. And then you say, OK, I'm going to respond. And you give it your IP address. So all of a sudden, someone connects to your server thinking they're connecting to WSFSbank.com. Bless you. And so now all you do is you just give them content to make them think they're connecting to that bank. And all you need is their name and password before they realize what happens. So you present them the login page, which doesn't change very much. And then they log in, name and password. The next page they see is blank, and then say, uh-oh, something's weird. Now you've just harvested their name and password, right? So that's why you need something called endpoint authentication. It's not enough just to say, connect to this website when I respond to DNS reply with an IP address. I want to authenticate with some sort of certificate that that really is WSFS, I can never say that fast, WSFS Bank's website, and you can insert whatever bank you want in that. You can also spoof a source address, right? You can pretend that you're somebody and exploit your DNS. And again, endpoint authentication is really, really important. Any questions about this? Now, I'm not going to pretend to be a security person. You can take a whole semester in internet security. I only talk at the level of network issues as far as internet security is concerned. I encourage you to take a full-blown cybersecurity course if you're interested in more detail about things like this. Okay, so let's take a look at peer-to-peer applications. Does anyone use BitTorrent? Or did anyone use LimeWire to save yourself from having to copy your legally purchased CDs, right? Yeah, because you wouldn't do that, other stuff, not this crowd. But nonetheless, peer-to-peer is really, really popular. And we're going to talk about torrents in particular and why peer-to-peer achieves the type of performance gains that it does. So again, a peer is an entity, a host or endpoint on the network that serves both the role of a client and a server. And it's not always on. Peer doesn't have to be always connected. Peers can come and peers can go. Sometimes it's called peer churn. Now, arbitrary end systems can communicate directly when you have peer-to-peer. You establish a connection, and now you're interacting directly with someone. In fact, peer-to-peer gaming was a huge breakthrough in internet gaming. Okay, and so things like Skype has peer-to-peer aspects, but BitTorrent was a particularly big win, making use of peer-to-peer's advantage, and we'll talk about what that advantage is and why that advantage arises. And so peer-to-peer is very good for very rapidly downloading files. And this figure depicts the scenario about the difference between so-called client-server communication and the advantage you get as a result of peer-to-peer communication. And so here we have a server, and the server is here on the left, and that server contains a file of size F. It doesn't matter what big F is, but nonetheless, it's the size of some object, and it's sitting here on an origin server. Now that server pushes that content upon request into the network, and it uploads it into the network, and we'll assume that the network is fast enough that it's negligible, the amount of delay for the network part. But when you're going from the access network for the server to get into the switching fabric for the network core, it's going to use a link that has an upload server capacity of U sub S, right? So U sub S, if U sub S is bigger, the server can push that file into the network faster. If U sub S is smaller, it takes a longer time for that file to be transmitted, uploaded into the network. And so associated with each peer, we have a host here. So this is the first one, first host, second host, third host, and so forth. So we have big N, many hosts. And when we talk about a particular one, we're going to use this index I. So I could be 1 up through and including big N. So we have N hosts, and on each of these hosts is running a peer. And so these hosts have connections to the network. They can both upload data or file into the network at upload speed U sub I. So that would be U sub 1 for the first peer, U sub 2 is the rate for the second peer, and so forth. Now, of course, these are different variables because depending on the connection, well, you might be on DSU wireless and now I'm on CIS Wi-Fi, and so my upload speed on CIS Wi-Fi is faster than upload speed on DSU wireless. And so each peer can have a different upload speed, right? So which is why in the book and in the diagram, they're labeled differently. Likewise, each peer can pull data from the network at a download rate, D sub 1 for the first peer, through D sub N for that nth peer, right? And so each peer or each process running both a client and server role can both upload data into the network, acting as a source, or download data from the network, acting as a sink or a client. Okay. So what happens when you try to distribute a file in a client-server scenario? Well, when you distribute a file, what does it mean to distribute? It means every single host or peer on the network, all N, many of them, receive a copy of the file. So in order to receive a copy of the file, they have to issue a request, and the result of that request is that this file gets downloaded off the server into the network and then downloaded into each one of those peers. So let's take a look at that scenario. So if we have N peers, that means N copies of that file are going to get downloaded into the network. And if we look at the aggregate amount of data we're talking about from the perspective of the server, that's N times F, because N many times that server, that origin server, is going to push its file, is going to upload that file of size F into the network. So that means N times F is the total amount of data that that server is going to push into the network. Now, of course, if the transmission rate for uploading, for that link, the upload link from the origin server into the network is U sub S, we take the total amount of data, N times F, and we divide by that transmission rate, U sub S. So the time it's going to take that server to push N many copies of that file of size F into the network is going to be NF divided by U sub S. Any questions about that? We're talking about aggregate. When they say deliver a file, distribute a file, it's the amount of times we have to send that file to every single copy or every single host on the network that needs it. Okay, so then when we take a look at the other part of distributing this file of size F, it's the amount of time that each client takes to download that file from the network into its own address space. And so again, we said that each peer or each host has a download rate of D sub I. So it's D1 for the first peer, it might be really fast. D2 for the second peer, maybe it's a little slower, up through and including D sub N. And so among those peers, one of them is going to have the slowest link, right? It doesn't matter which one it is, but one of them is going to have the slowest link. Now, in the book and in the nomenclature for the diagram, that slowest link is called D sub min. Right? And D sub min is just the slowest downloading client, the link to the client to download that has the lowest transmission rate, the smallest transmission rate. And so by definition, if you have the smallest transmission rate, you're probably going to be the last one to get that file, right? So maybe the other host is downloading at 20 megabit per second, you're downloading at 100 kilobit per second, right? You're going to be the last one to get that file. And so that file is not considered distributed to everybody until the last person gets it, right? And so if we want to know the total time it takes to distribute that file to all these n many clients on the network, it's going to be at least whichever one of these is greater. The time it takes to upload all the files, all the copies of the file into the network from the server, that's NF over U sub S, or the time it takes for the slowest client to download it, right? And that's going to be F divided by D submit. So the amount of time it takes in a client-server scenario to distribute this file is going to be at least the greater of these two quantities, NF over U sub S or F divided by D submit. Does that make sense? Any questions about this? No? No questions? Okay, let me do a time check. 12:53, thank you. So we're about 18 minutes. Okay, so let's take a look at the client server. Oh, yes, forgot this part. If you look at this, this scales linearly in n. What does that mean? It means if you have n many clients that need the file, let's say you have 6 clients, you add a 7th client, it's going to be 1 part longer. If you had 8 clients, it's going to be longer. It's in 9 clients. If you have a million clients, it's going to be a million times potentially longer. And so as you add clients, the amount of time is going to, as a straight line, it's going to go up and up and up and up. Let's take a look conversely at the client or the peer-to-peer version of this. So in a peer-to-peer file distribution scenario, you have 2 sources for every file that can be distributed to clients across the network. The file can come from the server, right? Because that's where it originated, or that file can come from another client, from another peer, right? And so not only do you have the server as being the entity that delivers the content, you also have other peers. The moment a peer has that complete file, it can now act as a source from which others can download the file. So let's take a look at this scenario. So we have the server. The server sends 1 copy of that file into the network. Somebody initiates the download. So that file is of size F, and the upload link for the server is at rate U sub S, the upload bandwidth of that link. Now, F over U sub S is the time it takes the server to upload. The moment that server uploads into the link, now any client or any peer that has a copy can now act like the server. You can have a second source, a third source, a fourth source, and so forth. So we also have the slowest peer, right? And we said dmin is the download speed from the network into a peer of the slowest download, right? And that's going to be, quote unquote, the last one who gets it. Now, remember that not only does the server deliver content, but other peers that have a copy of the file can deliver that content. And that's what this third term does. So the total amount of data we're talking about, because there are n many peers, and each one needs to get this file of size F, it's a total aggregate amount of data, n times F. That's the total load, if you will. Now, when we look at the transmission rate, or the rate at which data is delivered into the network, we have the upload speed of the server. Well, the server doesn't stop acting like a server, so it contributes U sub S as the total bandwidth at which it can push that data into the network as others request it. But then we also have this other term, this summation, and that's where the power of peer-to-peer networks comes into play. Now, each one of these peers has an upload rate into the network of U sub I. And so that's U sub 1, U sub 2, U sub 3, U sub 4, and so forth. So potentially, you can have n many peers, each of them acting like a server. And when a peer acts like a server, essentially, it's contributing its bandwidth, its upload rate, U sub I, towards the total amount of upload bandwidth available to anyone who needs that file on the network. And so we add to the upload rate or upload bandwidth of the server, U sub S, we add to it the sum of the individual peer upload rates, right? That's where that summation comes from. And so if we look at this for a peer-to-peer scenario, if you want to distribute this file of size F to all the peers on the network, one of 3 things is going to happen. We have the upload rate of the server, the transmission time, so that's F divided by U sub S, or the download rate of the slowest downloader, or peer, that's F over D sub min, and then the aggregate amount of data divided by the aggregate upload bandwidth, right? So that's NF, n many copies of this file F, and then potentially the server's bandwidth plus the upload rate of each of the peers. So we get this U sub S plus the sum of all the U sub I's, okay? Any questions about this? And so this property, this idea, has a name. It's called self-scalability. As you add more peers, right? Yes, the amount of data that you traffic across the network is greater because n times f gets bigger as n gets bigger, but you also increase the upload capacity because each peer that joins the network also adds upload capacity, can act like a server. Okay? All right. Any questions about this? No? So let's take a look at the following graph. And for this graph, on the horizontal axis, we have the number of peers, n, so those are integers, marked in 5 peer increments. So we can have 5 peers, 10, 15, 20, and so forth, even though on the individual ones it's marked. The markations in this graph are every 5. So that's on the horizontal axis. On the vertical axis, we have the minimum distribution time, right? That's the amount of time it takes this file of size F to make its way ultimately to every single entity, every peer on the network. And so the black line represents file distribution in the client-server scenario. That's where each peer or client downloads that file directly from the server. And one thing you'll notice, we have this line here that slopes upwards, and that's in the black. And as we increase the number of peers, the distribution time continues to increase, right? But if we look at the blue line, with these blue squares, that's the peer-to-peer scenario for file distribution. And with a peer-to-peer scenario, yes, you increase the amount of data that you're going to distribute at n times f, but you also increase the capacity. And what you'll find here is because each peer also brings with it service capacity, this graph, the blue graph, will come to an asymptote, meaning that eventually, as you add more peers, you're not going to get a discernible increase in the distribution time. And that's called self-scalability. While adding a peer also increases demand in terms of the needed bandwidth to distribute a file, each instance of a new peer also adds capacity. And so now you're loading from multiple servers with an aggregate increased total upload bandwidth. Does that make sense? Any questions about this? Okay. So let's take a look at file distribution in BitTorrent. All of that being said, BitTorrent consists of a peer-to-peer network, and it traffics in chunks of files. So you take a file and you chop it up into pieces. And the accounting list, if you will, that says, here's the file, here's the first piece, here's the second piece, here's the third piece, that's called a torrent, right? And so you have your torrent, which is an accounting of the chopping up of some file. Could be like a software development kit, could be a video, but this file is chopped up into standard 256 kilobit chunks, and you have this listing. And so now with BitTorrent, each of the peers, they're going to trade, if you will, by exchanging these 256K chunks. So if you have a lot of peers around on the network, you don't have to collect all of the parts of that file from one person. You can collect some parts from this person, some parts from that person, some parts from that person. And in aggregate, because of all of this aggregate upload speed of all the peers on the network, you might be collecting a very small part of this file from each person, but you have so many people, you're getting everything at once, and you end up with a faster download of that file of interest. So you have your file divided up into standard size chunks, and the accounting list of those chunks is called a torrent, and all of the peers in the torrent send and receive file chunks. And so you send to me a piece that I'm looking for that I might not have. I send to you a piece of a file, maybe a different file, maybe the same one that you don't have that you're looking for. And so all of this is managed through something called a tracker. A tracker is almost like a name and address book, right? When a peer comes online, it contacts the tracker and says, hey, I'm available, I'm ready to trade, this is how you contact me. So a new person comes along, a new peer, contacts the tracker, it gets a list of peers. And then it takes that list of peers it got from the tracker and it starts trading in chunks of files. So in the limit, as you get all these pieces, you're building up, building up, building up until eventually you have the entire file. Once you have the entire file, you can now choose to leave the network, or you can stay attached to the network and trade pieces of your file that you have with others who might need this. Okay? Any questions about this? Does that make sense? Yeah. Okay. So we have, this is what BitTorrent is. And in addition to file sharing, there are APIs out there where you can build on BitTorrent to implement all sorts of data storage mechanisms. Okay. So let's say Alice arrives, and Alice logs into her peer. She starts it up, and she obtains a list of peers from the tracker. She takes that list, and then she starts exchanging chunks of files with peers in the tracker. Now, of course, the scheme is that those pieces that get traded first are the ones that are the most rare, right? That don't exist as much. And so if you have a rare chunk, that's going to get given up first because that is the most constrained piece of the file, right? So Alice obtains the list of peers from the tracker, begins exchanging file chunks with peers in the torrent, right? The torrent is just the group of trading partners, if you will. So now a peer joining a torrent starts out, let's say you don't have any chunks of the file. You get the torrent, you have the accounting list, and now you join the torrent. So you contact the tracker, you get a list of peers. And you start out with no pieces of that file, but you know which pieces you need. And over time, you start accumulating these 256 kilobit pieces of the file from this partner, from that trading partner, from that trading partner, and so forth. And so you get a list of peers, and you connect to a subset of those peers, and those are called your neighbors. And so now you're looking for this idea of who's a good trading partner. A good trading partner is somebody who has things that you need, because pieces of the file that you don't have, you're going to exchange with that person. You're going to get a copy from that person using their upload capacity. So you're going to download units of these chunks of the file from your peers, but you're also going to keep statistics on who's a good trading partner, because the set of trading partners is going to change over time. You get a list of peers, but then you're constantly reevaluating who has what you need, who's a good trading partner over time. So you download, while downloading, you also upload to other people. So in addition to your evaluation of them as to whether or not they're good trading partners, they're also evaluating you. Are you a good trading partner? Do you have things that I need? Because it makes no sense to trade if you're never benefiting, right? If you're never getting something that you need. Okay, so peers can come and go. It's called peer churn. Maybe someone decided to, to close their laptop or not participate. And that could be because you have the file and you're done. Or maybe you just ran out of time. You decided not to stay. There are lots of things people can do. But nonetheless, you have a subset of peers. And out of that list of peers you get from the tracker, you're only going to trade with a subset of them. And that subset can change. You also request chunks. Now, at any given time, as you get more of these chunks of the file that you need, that different peers are going to have different subsets. So certainly in your evaluation of who is a good peer, that evaluation is going to change. So periodically, you ask your peers, your trading partners, do you have this list of chunks of the file? And they either say yes or they say no. If they do have a lot of them, then guess what? You're a good trading partner. And so Alice continually reevaluates her list of trading partners among all of the list of pairs that she has, and she wants to request from peers those pieces that are the most rare, they exist the least. So Alice sends these chunks tit for tat, meaning that she always looks at the peers that are sending her pieces of the file at the highest rate, meaning those who are the best trading partners. And every once in a while, she will reevaluate who are the top 4 trading partners. And if a different 4 are the best trading partners, she's going to switch, right? Alice is concerned about getting the pieces she needs. Now, of course, most of the time, a lot of Alice's peers are choked off or choked out, if you want to say it that way, because she does not want to receive or trade with people who are not effective. And so if you think about it, Alice knows jiu-jitsu. She likes to choke out her peers, right? Well, that fell flat. I have to think of new jokes this semester. All right. Anyways. All right. That fell flat. All right. So she chokes out most of her peers. and she only wants to trade with the top 4 trading partners. She reevaluates, and then she makes another decision. Now, machine learning, this is called exploitation. You're taking the data that you have, information you have, and you're making the optimal choice. In addition to exploitation, you want to do what's called exploration, right? Exploration is handled by a random selection. So while Alice chokes out most of her peers, she selects the top 4 trading partners, and she constantly reevaluates them to try to get the best top 4, because that means she can get the file pieces she needs. In addition to the top 4, she will randomly select someone as a trading partner, because the idea is that, okay, well, these are the top 4, maybe there's somebody who might be a little bit more promising in the near future. So in addition to this exploitation, maximizing on the top 4 trading partners, she also makes a random selection for some peer who's not among the top 4 and starts trading with them with the hopes that eventually that person might be even better than the top 4, right? Now, sometimes it works, sometimes it doesn't. When it works, great. That means Alice is always trying to try new trading partners to see if she can get better throughput as a result of that person or that peer. Does that make sense? Any questions about this? Okay. So that's called tit for tat. So let's take a look at how this works semantically. We have Alice and we have Bob, and Alice optimistically unchokes Bob, right? So she releases the bare naked choke, as it's called in jiu-jitsu, and she makes a random selection and picks Bob. Rear naked choke, not bare, rear naked choke. So she optimistically unchokes Bob, and then she starts training with Bob, and all of a sudden, she becomes one of Bob's top 4 trading partners. That was a fruitful, optimistic unchoke. Okay, so Bob then reciprocates and starts trading his file chunks with Alice. So now, Bob becomes one of Alice's top 4. This randomized choice was fruitful. And now they're both exchanging these 256 kilobit chunks. Okay, so if you have a higher upload rate, among your trading partners, you can, in aggregate, get more of these 256 kilobit pieces, and that results in getting your file faster. Okay? All right, any questions about this? Does that make sense? Okay. So let me end with this YouTube video about BitTorrent, and this will bring home a lot of what we're saying. Let me do this. The volume. Volume.
Aren't like they used to be. These days, short HD video or computer files aren't like they used to be. These days, short HD video can be over a gigabyte in size. That's huge. The problem is that the bigger they are, the harder they are to share. Thankfully, we have options that make sharing big files over the internet fast and easy. This is BitTorrent Explained. Blake was so excited. He's the president of his local Sasquatch fan club and recently heard that a new video was circulating. He couldn't rest until he had that video on his computer. He tried to download it from the original website, but it was painfully slow. Because so many fans were trying to download it at the same time, the website crashed. He was discouraged. Then, to fellow fans, the video could also be downloaded via BitTorrent. She said that unlike typical downloads, files using BitTorrent actually download faster when more people are involved. And it works with any kind of file. To see for himself, Blake downloaded BitTorrent, the world's most popular BitTorrent app from uTorrent.com. He opened the program and was a little confused. There were no videos, and he wasn't sure where to start. But soon, he realized that's because BitTorrent is a little like a web browser. Just like a browser needs websites to be useful, BitTorrent needs special files called torrents to work. A quick web search pointed him to websites with torrents galore. Soon enough, he found the Sasquatch video torrent, downloaded the torrent file to his computer, and with a simple click, uTorrent immediately sprang to action and the file started downloading. He could see it was working and wondered how. Later, his friend made it clear by talking about how downloads typically work without BitTorrent. When someone downloads a file, it comes to their computer in a stream from a single source. When multiple people want the file, that single source can get overworked and can even shut down. BitTorrent solves this problem by making each downloader a source. This way, they get pieces of the file, but also provide pieces to each other. Together, the downloaders become a network of multiple sources, all working to provide pieces to one another. This makes downloads fast and reliable. A couple of things behind the scenes make it happen. First, when he clicked download, Blake received a torrent file. This file has all the information about the video file, like what pieces are needed to complete it. But something is missing. Blake needs a way to connect to other users who have the pieces he needs for his file. BitTorrent uses a computer called a tracker that helps Blake's computer find other computers called peers. The tracker keeps track of computers that are downloading or already have the whole file and introduces Blake's computer to them. With the connections in place, he receives what he needs and also distributes pieces to others who are also downloading. Blake got it. BitTorrent works because it turns downloaders into sources, and more downloaders means more sources and faster downloads. In the end, Blake's video downloaded in no time at all, but he was a little disappointed. What he thought was a Sasquatch was only a loop. But at least he now knows with BitTorrent there's a faster, easier way to download files from the internet.
Okay, YouTube. There we go. All right. So let me take a time check. Yes. Now let me end there. It's 1:14. So we'll pick back up with hopefully the balance. We'll talk about content distribution networks and the Dash protocol for video streaming. And then we'll also have a socket programming example, both for a connection-oriented service TCP and the connectionless service UDP. So I will see you all on Thursday, and I look forward to your solutions for the project tonight. I'll see you Thursday.